Yes.
Okay, we may shall start now. Assalamualaikum and a very good morning to all participants. Welcome to workshop on analysis of rubber without using instrument. Before we start our program, there are a few announcements that I would like to make. First, make sure your microphone is mute during the session except for the Q&A session. You are encouraged to turn on the camera during the workshop. If there are any questions, you can click on the raise hand button or you can write on the chat box so that our committee would notice and help you. Make sure everyone is signed in to the Microsoft Teams to access the chat box and the Q&A. Our program will start sharp at 9:10 a.m. and I hope everyone will stay tuned until the end of the program. The Honorable Prof. Dr. Haja Farida Zuraina Muhammad Yusuf, Faculty of Applied Science Dean. The Honorable Prof. Dr. Chan Chin Han, Postgraduate Chemistry Club Advisor, Universiti Teknologi Mara. The Honorable Dato Dr. Sun Tikwe, President Institute Kimia Malaysia. Dr. Hwee, Technical Trainer and Consultant at K&W Training and Consulting, our invited speaker, and our lovely participants. Ladies and gentlemen, Assalamualaikum warahmatullahi wabarakatuh. Welcome to workshop on analysis of rubber without using instrument. I am Miss Nashiba, your master ceremony for today's program. Ladies and gentlemen, now we will start our program with the national anthem, Negaraku and UiTM official anthem, Wawasan Setia Warga UiTM. Now, I would like to invite Mr. Ahmad Hafiz to recite the dua.
Assalamu alaikum wa rahmatullahi wa barakatuh. Before we start our webinar today, let's pray together. May our webinar running well. أعوذ بالله من الشيطان الرجيم بسم الله الرحمن الرحيم الحمد لله رب العالمين والصلاة والسلام على أشرف الأنبياء والمرسلين وعلى آله وصحبه أجمعين. Ya Allah, Ya Rahim. Praise be to God, to the Lord of the worlds. Peace and blessing be upon our Prophet Muhammad sallallahu alaihi wasallam and his companions, and for those who followed his example till the judgment day. Allahumma ya Allah. On this blessed morning, in conjunction with the workshop on analysis of rubber without using instrument, we beseech thee and grateful toward you in favor of all the infinite blessing to us, your humble servant, to life and safe and prosperous life. We seek your blessing for flawless progress of this event from the beginning till the end. We seek your guidance to steer clear of event that will determinate the progress of this event. Ya Latif, Ya Rahman. Please bless us with your tawfiq and hidayah. Please guide Faculty of Applied Science, UiTM Sahalam, to the greatness, peace, glory, and prosperity in this world and hereafter. Make us responsible intellectual. Grant us with the valuable knowledge that will be beneficial to mankind in order to gain your mardatillah. Make us your righteous servant that followed your commands and neglect the sinful act. Please forgive us for our wrongdoing. Ya Muzil al-Barakat, bestow peace to our beloved country, Malaysia. Preserve us from any threat and disaster, neither man-made nor natural disaster. And to you, Ya Allah, we ask for security and prosperity upon us, our leaders, our country, peace to fashion in us in order to face the challenge from you. Please accept our deeds and please reward us accordingly. ربنا عليك توكلنا وإليك أنبنا وإليك المصير. ربنا آتنا في الدنيا حسنة وفي الآخرة حسنة وقنا عذاب النار. صلى الله على محمد وعلى آله وأصحابه وسلم والحمد لله رب العالمين. Wassalamu alaikum warahmatullahi wabarakatuh.
Thank you, Mr. Hafiz, for the dua. To kick off this morning's program, we are pleased to have with our Faculty of Applied Science Dean, Prof. Dr. Hajah Farida Zuraina Muhammad Yusuf, to deliver the welcoming remarks.
Assalamualaikum and very good morning to all of you. Thank you, Ms. Shiba, for hosting today's workshop live from Bilik Seminar Al-Khwarizmi Bangunan Sarjana UiTM Shah Alam. Firstly, thank you to all of you for being here today. On behalf of the Postgraduate Chemistry Club, PCC, I, as the Dean of the Faculty of Applied Sciences, would like to welcome all of you to this workshop on analysis of rubber without using instruments. I would like to welcome our guests and speakers from Institute Kimia Malaysia, IKM, and KNW Training and Consulting, and all participants from other universities, companies, and industries. Some of you might be from other countries, having a different time zone, and I'm very pleased that you decided and accepted our invitation to be with us today. Our Postgraduate Chemistry Club PCC in short advisor, Professor Technologist Chemist Dr. Chan Chin Han, and the committee took the initiative to conduct this event because the previous workshops were graced with positive feedbacks from students, lecturers, and participants. This workshop is the results of collaboration between PCC, IKM, Institute of Material Malaysia, IMM, Plastic and Rubber Institute of Malaysia, PRIM, Kinematic Resources Sdn Bhd, and Bruker Malaysia Sdn Bhd. I hope this collaboration could extend our networking, as I believe with great networking we can give new and extra exposure to the lecturers, students, staff, and even the community. The goal of this program is to increase the understanding of students and researchers on the knowledge of some commonly used techniques for the rubber analysis without involving the use of equipment. The techniques are suitable for both academicians and students working on rubber, as well as those working in the rubber industry. In addition to the lecture, this workshop also includes demonstration sessions so that the participants could learn the practical aspects of the lecture content. Finally, although we are unable to meet physically, I hope we will still be able to communicate with you throughout this workshop, and may this workshop give a huge benefit to each and every one of us. Thank you.
Thank you, Prof. Dr. Hajah Farida Zuraina Muhammad Yusof, for the special opening message. Now, I would like to invite Dr. Soon Tin Kwe, President Institute Kima Malaysia, to deliver the welcoming speech.
A very good morning to all the participants, including the trainer of this virtual workshop on the analysis of rubber. This workshop is generally organized by Institute Kimia Malaysia and UiTM, UC, Teknologi Mara Malaysia, Postgraduate Club, and the purpose is to expose to the participant the very important aspect of analysis of rubber without using instrument. We are very fortunate to have a very experienced trainer, Dr. Hwee, who have more than 30-year experience in the rubber industry. Since most of you are chemistry graduate students of UiTM, I would like to share with you a little bit information of chemistry in Malaysia and Institute Kimia Malaysia. Institute Kimia Malaysia, or IKM, is registered with the Chemist Act 1975 under the Ministry of Science, Technology and Innovation. So we are actually a professional scientific body, all right, controlling the analysis of chemical and other materials in Malaysia. So if you graduate as a chemistry major, then you are qualified to join IKM as a member. We have developed over the past 50 years to be a very strong and influential scientific organization. We have many programs, including scientific conference that emphasize on the advancement of chemical sciences, CPD courses, that means continuous professional development program to train our chemists and other technologists in chemistry. We also have a social program at Malam Kimia, and also including our annual general meeting. So IKM plays a very active role in the development of chemistry in Malaysia, in training chemistry professional, and also in promoting chemistry education to school. So we have for school children, we have this K3M, or Quiz Kimia Kebangsaan Malaysia, which is very popular among secondary school students and the pre-university student in Malaysia. This workshop emphasized on the analysis of rubber, which is a very important primary commodity produced by Malaysia. And we are #1 in the world in terms of producing rubber glove, as all of you should be aware. So I think the workshop will provide very useful material for the student in the study of rubber as a polymer and also its application. I'm sure you'll benefit from this workshop, and on behalf of IKM, I want to thank UiTM Postgraduate Club for joining organize this event with us, and then for the trainer, right? The trainer who have spent time to conducting the training, and then to all of you, and I hope that you benefit or gain some important knowledge from this workshop. Thank you very much.
Thank you, Dr. Sun Tikwe, for the great opening speech. All right. I know for sure everyone is waiting and excited for this session. So, may I call our invited speaker, Dr. Hwee, for the first lecture.
Good morning. Thank you, MC, for the introductions. So before I start, there will be quiz questions to be answered by the participants. So I hope you have, if you wish to participate in the quiz session, I hope you have downloaded the apps. I think the link was sent to you earlier. And just to remind you that each participant can only win one prize. Okay. So after the question has been asked, I will allow 5 minutes for everybody to think about it, or if you know the answer, you can send immediately. So the fastest person who get the answer right will win the prize. Okay. So the result will be announced after the 5 minutes time. And then once you are the winner, so I think there's no need for you to participate in the following questions, because each person can only win one prize. Okay, I hope this is clear. Okay. So I will share my screen. Okay, so I hope everybody can see the slides and it's moving, right?
Yes, it's moving.
Okay, but sometimes it's not moving. Then I keep on talking, and at the end, people remind me that it's not okay. So the objective is to introduce some simple experimental analysis without using instruments. As an introduction, why do we don't use instrument, or if we have, maybe sometimes we don't use it, or because normally instruments are quite expensive in Malaysia, maybe due to our weak currency and we have to import them, so normally it's expensive, right? It's not so affordable. Even for example, GPC, HPLC, all this will cost more than at least 100,000 to 200,000. Some can be up to 300,000 ringgit. So they are very expensive, and also expensive to maintain. Okay. because you don't have the expertise, sometimes breakdown, you need to call in the technicians, So can be quite expensive for parts displacement or repair, and can take a long time. Also for factory, normally expensive instruments are not available in a production factory. Okay, normally expensive instruments are only available in R&D center. So for factory, normally they do not have. So what they normally do is just do a simple test. They have a simple one, maybe UV spectrophotometer, So those are frequently used instruments, but more sophisticated and more expensive instruments are normally not available in the factory. And sometimes we don't use it frequently. That's why we don't have. Because there's no point buying an instrument where you don't use it frequently. So it's a waste of money, right? You only use once in a while or only use for certain project. So once the project is over, you don't use it unless the instrument is your area of expertise. Okay. For example, if your research focusing on molecular weight, so maybe it's good to get a GPC, gel permeation chromatograph. That will be helpful. Otherwise, sometimes we go to other lab or we send to other laboratories, ask them to help us to do the analysis, or we send to the commercial laboratory. And sometimes we have the instrument, but then we don't have the operating procedures. Maybe we inherited the instruments from other people. So we may not have the procedure available to know how to operate. Or the operating procedure could be too complicated. It's too complicated, it takes a long time, so we don't use it. We rather use a simple kind of non-instrument type analysis. Last but not least, not technically competent to operate. Some of the instruments are quite complicated, and you need to have some experience before you can operate it without any issues. So of course, these are some of the common reasons, because there are other reasons, okay. And just a cautions to the participants who try the experiments introduced here for the first time. You need to take all the necessary precautions to ensure that it is safe to conduct the experiments. Okay. And secondly is to wear the necessary personal protective equipment, such as goggles, gloves, and lab coat, and so on. Okay. And make sure that the area is well ventilated because you are using solvent. Okay, and if it's not in a fume hook, you have to make sure that they are well ventilated. And make sure that no one is using any naked flame. Okay. When using solvents. So you probably need to put a notice, okay, or a warning somewhere nearby. Make sure that no naked fire is used because even though it's a distant away, sometimes it can also due to the fume of the solvent, it can also cause fire accident. So need to take note of that. And lastly, always have a second person ready to help in time of emergency. Okay? So for all laboratory work, you don't normally work alone. Work alone sometimes can be quite dangerous. So these are some of the precautions before you want to consider doing the experiments. Right. Okay, the first experiments we are talking about is a very simple one actually. You will notice it's a very simple experiment. Some of you might have used it before, and for those who have not used it, and you will be surprised how simple is it to determine the density of a rubber. So of course, the objective is to determine the rubber density with a simple experimental setup. Probably you are aware that density parameter is used in calculation of many other parameter. Example, if you want to know the volume, you want to know the volume fractions, you want to know the weight, all these, you know. Indirectly, you cannot measure, okay? So you have to use the density data to calculate. So the method is actually based on ISO 2781 methods. Okay, if you are interested, you can refer to the standards. And you probably heard of this Archimedes principle. Okay, so the density measurement is all based on this principle, which I will explain to you later on. So there are actually many methods in this density measurement. The easiest one, of course, is the suspension method, whereby you suspend the solid rubber in a liquid, okay, and then you just measure the weight. Of course, you need to have a balance, okay. So in that sense, some form of measuring device is needed. There are other methods like pygnometer methods and also the mixed liquid methods, which I will also briefly describe here. But among the three, the easiest one is the suspension of the solid rubber in liquid. Okay, so this is the explanation of the Archimedes methods. For example, you have a load of 5 kg, okay, and this is, let's say, the liquid, any liquid, you can mostly water, okay. So you submerge the load fully into the liquid, and because of the increase in volume, all right, and then the extra volume will be displaced here, okay, it will be displaced here. So there's a buoyant force here, you know, according to Archimedes principle. So because of this buoyant force, there will be a weight reductions, okay, after you immerse the load into liquid. And of course, you can notice the volume of this load is actually equal to the volume of the liquid displaced. And the buoyant force is equal to the weight of the liquid that being displaced after immersing the load into the water. So any object that completely or partially submerged in the liquid or gas and at rest, so there is the upward force we call buoyant force, okay, apply onto the object, okay. And therefore here initially we have 5 kg of load when we weigh in the air, but after immersing in the liquid, you can see there's a reduction of 2 kg. And this corresponds to the 2 kg of the weight the displaced water weight here. And of course, logically, the volume of the water is equal to the volume of the load here, right? Because it increase the volume of the liquid here, and then the extra volume actually is displaced by the water here. So this is quite common sense, but the new information here is the buoyant force is equal to the weight of the liquid displaced. So if it's partially submerged, then you will be up to the level of the surface, okay? And of course, the weight loss will be up to the part that is underneath the liquid. Okay, the part that is in the air will not be counted. So if you move the object out, you will see the load will increase. The balance here indicate. Okay, and of course, the water displaced will reduce. Okay, so I hope you are clear. Okay, you're clear with the Archimedes principle here. Okay, so before I introduce the suspension method, there's another method called pyknometer method. So the principle is the same. Okay, so the weight lost in the liquid equal to the weight of liquid displaced. Okay, and it's equals to the density multiplied by volume of liquid displaced. So, for example, you have the weight in the air, okay, and you have a liquid here in a pyknometer. So, when you place the solid object into the pyknometer and you cover it, which means it's similar to here, right? So it's the same that you displace the extra volume of the liquids, okay? And therefore you take the weight of the object in the air and without the object and with the object. Okay. So the volume of the before that, the weight loss of the liquid is equal to the mfw, this one, the original weight, okay, minus the difference between the weight with the object and the weight in the air. Okay, so this will be the weight loss in the liquid or the weight of the displaced liquid. Okay, and to get the volume of the rubber, you just divide it by the density of the liquid. Okay, here's the density of liquid. So since you know the density of the liquid used, and you also know the weight of the object or the rubber in the air, you weigh in the air. So the density will be the weight in the air divided by the volume of the rubber. Okay, volume of rubber is given by this calculation. It is suitable for object with the density higher than liquid. Okay, because we need the FWP here to be higher than here. Okay, because if it's lower, then you float to the top. So anything you float to the top, the weight will be the same. Okay, so you can't really. Of course, if it's suspended, then the density of the rubber is equal to the density of the liquid if it's suspended. But if you float to the top, then it's lower than the density of the liquid. You can watch this over YouTube where they can determine the density of sand, or if it is sand, very difficult to measure the density, right? Very difficult to know the volume, right? So what they did in the YouTube, they fill this one with sand, okay, So they determine the weight with the liquid. And from there, they can calculate the density of the sand. Okay, because sand is very irregular in shape, so it's very difficult to measure directly. So you got to use the indirect method. Okay. So the second method is the suspension method. Suspension method is very easy. Okay. Now, just now we saw the Archimedes methods where, the Archimedes principle, where you immerse the load and you have water displaced out, right? So you have a weight loss equal to the weight of the water displaced. Now, the second method actually shut the side drain here. Okay, so when you don't have a side drain here, so this liquid will not flow out, right? This liquid will not flow out. So when this liquid will not flow out, you have increase in weight, isn't it? When you immerse your load into the liquid, generally it's water. Okay? So if you shut this side drain, so the 20 kg of water will not be out from the container. Okay, so of course there will be increase in the weight of the total liquid here, and then the volume, the increase in volume, of course, is equal to the volume of the load. So this is the second method. Okay. So you just measure the increase in the weight when you suspend the rubber or any solid object in the liquid, okay, by not allowing the liquid to flow out. Okay. So experimentally wise, we measure the weight in the air as usual. Then we measure the increase in the liquid weight, okay, when we suspend the rubber in the liquid. So the increase in weight is equal to the weight of the liquid displaced. As I mentioned, instead of letting it flowing out, we allow it to increase. Okay, so we measure the increase in weight. Okay, and so the volume of the rubber is equal to the volume of the liquid displaced. So the volume of liquid displaced is equal to the increase in the weight divided by the density of the liquid. Okay, and then since we know the increase in the weight, we know the density of the liquid, so you can know the volume of the object, or rather the rubber. Okay. So the density of the rubber will be the weight we measure in the air divided by the volume determined here. Okay. So this is the second method. It's very simple. So you don't need to have a pygnometer in this case, right? Because pygnometer sometimes may not be easily available also. Okay, so this is a simple method without the need of using pygnometer. Okay, the third method is a mixed liquid method. Okay, so first you choose a liquid that with the density, two liquids actually, two mixable liquid, one the density higher than rubber, the other one density lower than rubber. So you mix them and then you let the rubber suspend, let the rubber immerse in the liquid. So you mix them gradually until you see the rubber suspended in the liquid, the mixed liquid. Okay. For example, you use, let's say, chloroform and methanol. Okay, so chloroform density higher than rubber, methanol lower, so you mix them. So until the rubber is suspended in the mixed liquid. From there, you measure the density of the liquid, which is by a pygnometer. Okay, so the density of mixed liquid will be the same as the density of the rubber. Okay, so this method actually need to use pygnometer also, but it's a bit messy, right? You need to use solvent. Somehow you need to use two solvent. One is higher than rubber, the other one lower than rubber density. So not, I would say, not commonly used. So now back to this one, okay? Back to this one. What happens if the rubber that is floating on top, it doesn't suspend, it doesn't become suspended in between. So you need to pull it down with the load first, okay? With the load that you can pull it down. I'll show you in the video, okay? You pull it down so that it becomes suspended in between, okay? Suspend in between. From there, you can measure the, or else the rubber will float on top, then it's not accurate anymore. But if the rubber floating on top, then the volume displaced will be equal to the part that is submerged under the water. The parts that on top in the air one will not be counted. Okay. So we need to be fully submerged in the water. Okay. So it's a rather simple method, isn't it? So for those who have not tried this before, you can try. It's a simple methods. Okay. Okay, some practical notes here. First, the rubber sample must not absorb the liquid used. Okay, it cannot absorb and then it becomes swollen. Then the method should not be used. Oh. For example, let's say you use chloroform, it can be absorbed by natural rubber, so you shouldn't use. Maybe you should use methanol and water. Okay. Lower surface area better. Okay, so we should not have a very high surface area because somehow an object will somehow absorb a little bit of liquid, right? No matter what. So the lower the surface area, the better. So the absorption will be lower. Anyway, the time taken to measure is very short, so should not be a problem. And secondly, the rubber sample must not trap air bubbles. So if you trap air bubble, then the density will become lower, right? Because air bubble is lighter. So we give you what you call lower reading. Okay, make sure you do not trap air bubbles. Density is a temperature dependent property. Okay, so when the temperature is high, the density will be lower. If the temperature is low, the density will be higher due to expansion and contraction of the object. Okay, so you need to take note of that. Okay, so you need to be consistent. If you need your data to be at room temperature or at certain specific temperature, then you got to measure the density at that temperature, or else sometimes can be depending on your requirement. If your requirement is very stringent, you want to have less variations in your calculations, then you have to specify or you have to do it at specific temperature, right? For pygnometer methods, object density should be higher. Okay, as I said, if the object density is lower, then all sample will be the same, right? You will not get any difference. Okay. Okay. So that conclude our first part of the presentation. Now I'll show you the density measurement. Okay. So I only show you the suspension method where it does not require the use of pygnometer. So to make, could you hear the sound?
Yes, yes, it's clear.
Okay, okay. Sometimes it's not working, so I just want to make sure. So to measure the density of the rubber, first we prepare something like this. We have a load to pull it down, and then we have a clip, paper clip to clip the sample. Okay. Okay, so this is water and its density is higher than the rubber. We need to sink the rubber and suspend it in between. So first we put in weighing balance. All right. Okay, and we press 0 to 0 it. After that, we clip the rubber. So okay, so we hang the rubber test sample piece clip on the paper clip, and then we dip in again, and we measure the increase in weight again in the balance. Okay, very simple, right? Just a very simple process. You can see from there you can get the density of the rubber. Okay. Okay. So now is the time for quiz. Okay. Time for quiz, and I'm going to show you the questions. Or is MC going to show? I show, right? Okay.
Yes, yes. Doctor, the one show it.
Okay. Question number 1. In the diagram below, what is the weight registered by the weighing balance when a 5 kg is being suspended in the water? Okay, so you just need to answer what is the question mark kg here. So let's say you put a balance here, 20 kg. Okay, so when you immerse the load here, what will be the weight here? Because the displace is 2 kg here. Okay, so this is question 1. Okay, you just choose A, B, C, D, any answer that you think is correct. Okay. Second, if the weight of a load in the air is 500 gram, the volume of the liquid with a density of 0.9 gram per centimeter cube displaced on a container is 300 cc or centimeter cube. When the load is weighed in the liquid, what is the weight of the load in the liquid? Okay. So as I said, you can answer by at the app there, mentioned earlier on. So I allow 5 minutes from now. The fastest person will get the prize. Okay. This is question 1. This is question 2. Maybe I copy into one better. All right, I think 5 minutes is over, right? It's a very simple questions. Okay. So for question 1, question 1, since it is above the is a suspend, anything that is suspended or on top of a liquid will not have any weight. Okay. So the balance you will still register 20 kg. Okay. Only when it's sink to the bottom, only it registers some weight. Anything
Doctor,
is yes.
Doctor, sorry I interrupt, but there are some they cannot answer the question yet.
Why?
Wait. The quiz just started.
Oh,
I just started the quiz just now.
oh, okay.
Sorry.
I thought the 5 minutes is allowed them to answer.
Doctor, can we wait another 2 minutes?
Okay.
Okay, thank you.
So
Sorry, Doctor,
MC
we have the
winner.
we already have the winner.
Okay, so you announce lah.
Okay. I will share the screen for the leaderboard.
But you check with Nabila, is it? Should it be shown?
Yeah. All right. Now we have the winners. We're gonna have top 2 winners for this quiz, experiment 1. The first winner is YY, and the second one is Jia Nian Tan. Congratulations for both winners. The winners, if you can access the chat box, please provide your full name and phone number. If you cannot access the chat box, please open your mic.
Okay, okay. Thank you very much. So now I explain a little bit. In fact, I explained halfway. I didn't know it was not ready. Okay. So anything that is suspended. Sorry. Before that, to get ready the second. Okay, I think I just explained halfway, never mind. Consider it's a bonus. Anything that is floating or suspended will not contribute to the weight, okay? Unless there's an increase in the volume. Since this one is already displaced out, so there will be no weight increase. So it's the same as the original weight, okay? Second question, of course, is very simple because the volume that displays out is 300. So the weight loss is 270, right? So obviously, the weight in the liquid is 230. Okay. Okay. So anybody has any questions? I open the sections for Q&A. Anybody have any questions? Any questions? No questions. Maybe I explain a little bit here. Yeah. You see why we use this formula, because this will be the weight of the liquid plus additional weight of the load in the liquid, right? So this is the weight of the load in the liquid plus the weight of the liquid here, because anything that is in the liquid will be the same as the original liquid plus the increase in the weight. Okay. So when the rubber density is higher than the liquid, so it will give you register the weight by the weighing balance. Okay. If it's floating to the top, then there will be no weight. Okay. If floating to the top or suspended, then the weight of this third pygnometer will be the same as the second pygnometer. So from here you can work it out. Okay, the difference here is actually the weight of the liquid displaced. Okay, the weight of the liquid displaced, because this MFWP is equal to MFW plus the weight in the liquid. Okay, so you subtract the weight of the liquid off from the original weight, you get the weight loss. Okay, so when you get the weight loss, you will get the volume of the volume of the liquid by dividing it with the density. Okay. Yeah.
Doctor, there are participants who want to ask a question.
Oh, okay. Is it in the Q&A then?
Yes, somebody raised a hand just now.
Yeah.
There is one question. In Archimedes principle, the object submerged in water is supposed to be the rubber or something else.
Oh, of course, it's a rubber. As I show you in the video, the object that we immerse or submerge in the liquid is the rubber. Or it can be anything actually. If it's a plastic, you can also measure, not necessarily rubber. You know, it is a sample that of higher lower density than rubber on the liquid. Then you need to pull it down. Okay, into attach a load. Okay, as I show in the video clip. Okay, I hope it's clear.
Okay, thank you, Doctor.
Okay.
Okay, Doctor, we have other question.
Okay.
Okay. How do we calculate theoretical density of rubber? From Razif.
Theoretical. I don't understand what is by theoretical. You can measure it. Over here is we measure the density of the rubber. You know, theoretical. Frankly speaking, I have not come across calculating the density of rubber theoretically. You know, it's more because density, you can measure directly. Okay, or you can measure the weight, you can measure the volume. That's to get your density. There's no need to measure it theoretically. You know, I mean, you measure the weight and you measure the volume. You theoretically you're calculating the density, right? Theory, so to speak.
Okay. The next one is, what is the minimum weight required for dry rubber to measure the density of rubber using suspension method? Minimum weight of dry rubber.
There is no minimum weight actually. The minimum weight will be the accurate reading you can get from the weighing balance. If you have a very accurate weighing balance, let's say up to 4 decimal point or 4 decimal places, I think 1 gram should be enough. Actually, there's no minimum weight. The higher the better, of course, because the as I said, the absorption of the liquid will be lower, right? And then your moisture, all this will affect the moisture absorption, all this will affect your reading also. So I say larger sample will be better. Okay. I think 1 gram is good enough, you know, to get the density. But of course, if you can get maybe 3 grams, 5 grams, or 10 grams, will be better, you know. Because the higher the weight value, the lower the uncertainty or the error. When you have a very small object, then the absorption of moisture can be high or the liquid. Any more?
Okay, Doctor. What is the difference between actual density and theoretical density that will give free volume of vacuumized rubber, and how does it related to the mechanical properties?
Oh, this is already out of the topic. Actually, we do not discuss free volume here today. Okay, so you'll be too complicated to explain. We only discuss about the density measurement here. Okay, if there's no question, I will continue. Maybe I explain a little bit here. Okay.
Doctor?
Yes.
Sorry, we have a last question.
Okay,
this one asks for the question for number 2, quiz number 2. If the load is 500 gram and the volume displaced is 300 centimeter cube, the density of the load will be 1.67 gram per centimeter cube. Will the load suspend or sink to the bottom?
Again.
If the load is 500 gram and the volume displaced is 300 centimeter cube, the density
okay.
1.67. Will the load suspend or sink?
Then you work
bottom?
out. Let me go back.
Quiz number 2, I think.
Okay. So it depends on the okay, you calculate the density of the, I didn't calculate the density, okay? Okay, 500, so 500 divided by 500 gram, right? So the 500 divided by 300, so it should be higher than 1, so you will sink, right? 500 divided by 300, that will be the volume, volume displaced. So the volume of the load is 300. The weight is 500. So 500 divided by 300 is higher than 1. So it's higher than the density of the liquid, so you will sink.
Okay, Doctor, there's a participant named Zaifa Surya. She maybe has a question to ask. So Zaifa Surya, you may ask a question.
Yes, good morning, doctor. I'd like
Morning.
to find out, let's say, morning, I'm Mr. Yu, actually from Kinta Rubber Works Ipoh. If let's say the density of the polymer is porosity and is definitely less than 1, how do we measure actually?
Oh, less than 1, you have you seen the video clip just now?
Yes. I see.
Yeah,
Yes,
you just according to the video clip, you just zero it with the load, okay? Then you attach it so that the load will pull it, become suspended in the liquid. Then you can measure the increase in the weight, of just show in the video clip.
But in the event, let's say the rubber itself has a lot of porosity, because when you mix rubber, there are a lot of porosity inside. Let's say it's a not highly loaded compound, it's less than 1.
Then
there's still porosity.
you have to squeeze out the air already.
Because it's very nervy and quite difficult to squeeze out.
Yeah, you got to maybe use a hot press to squeeze out the air. There's no choice because
no choice. I see.
Yeah, you have the air inside. How to determine the
quite difficult. Yeah.
Quite difficult. Yeah, you got to use. I agree.
Quite difficult. Yeah.
Yeah.
Yes.
Like foam.
Because we need to. Sorry. It's okay. I think just want to share the experience as well. Thank you. Thank you.
In that case, you need to use a hot press to press the lid to squeeze out the air. Hot press to soften the rubber, and then
we put inside to cure the compound, right? Is that what you meant?
Sometimes
if it's a master batch without purity.
Sometimes we have a hot press to soften the rubber, and then you squeeze out, press the air out. From there you can measure, okay, the density of the rubber without the air,
I see.
Yeah.
Okay, we will try that and see. Thank you. Thank you.
Welcome. Any question? Any other questions?
There's no more question, Doctor.
Okay. Just now I was trying to explain this. Maybe it's not so clear to you. Okay, so you have actually this one actually equal to M F W, okay, plus weight. Okay. Okay. So weight in liquid. Okay. So you cancel off this one. MFW minus MFW, you get 0. Okay. So you get this minus you get plus, right? So you MP minus weight in liquid. Okay. Will give you the weight loss. Okay. This is what I was trying to say. I hope it's clearer to you now. All right, we continue. Okay. The next one is a little bit more a little bit more complicated. Okay. The next one is a crossing density using swelling method. You will be probably have been using this for a long time. So to determine crossing density rubber using solvent swelling method, so rubber require crosslink to enhance the mechanical and chemical property for longer service life. Increased crossing density will not enhance rubber indefinitely, rubber performance. There will be certain optimal level of crossing density. Okay? So it doesn't mean crossing density, the higher the better. Okay. The example are given in the next slide. Estimation of crossing density is essential for product performance and service life. So for example, the change with the crossing density okay. For friction, of course, we decrease crossing density. Okay. Partner increase with increasing crossing density. If you talk about tensile, tear strength, toughness, vertic line, or this, there's a max optimum level of crossing density. Okay, because it will increase to a maximum value and then it will decrease as the crossing density increases. Okay. So crossing density is a measure of crossing point per unit volume. Okay, so normally it's in mole per cm cube. You can also express in mole per gram. So there's another parameter called MC. MC is the average molecular weight between two crossing points. Okay, between two crossing points. So normally we express in gram per mole. So the correlation between crossing density and the MC is given here. Okay, where the rho is the density of the crossing rubber. Okay, phi here is normally either tri or tetra functional. It can be more than that. It can be penta also, pentagon, depends. If it have a cross linker with a star shape, then it will probably give you a higher functional cross network. Okay. So for example, if let's say it's a tetra functional crossing point, then you get 4 here, right? 4, then this will equal to half of the MC. Okay. Principle. So when we soak the rubber crossing rubber in solvent, it will swell because of the rubber has lower osmotic pressure, right? So the solvent has very high. So the solvent will flow into the rubber and will expand. Okay. Of course, only when the rubber can swell in the solvent. Okay. If not, of course, you have limited swelling. So it will swell to certain until the extent that the elasticity of the rubber will restrict further expansion of the crossing rubber. Okay. So it's related to elasticity of the rubber. Okay. So when they are in equilibrium, this way we can measure the crossing density. Swelling ratio, S3 is equal to solvent volume divided by dry volume. Okay. So is also equal to 1 over VR. VR is the volume fractions in the solvent rubber. Volume fraction meaning what is the fraction or fraction of the solvent in the solvent state. Okay. So the solvent volume of course is volume of the solvent plus the volume of the rubber, right? But we cannot measure the volume directly, so we have to use the weight and the density data. Okay. So when the osmotic pressure in the solvent in the solvent rubber pi is given by this equation. Okay. Elasticity of the rubber is given by this equation. Okay. So we can actually simplify it. Okay, we can actually simplify it. When in equilibrium, the elasticity equal to the osmotic pressure, right? So we have these two in balance. And because the VI is very small than 1, so we can simplify it into these equations. Okay. So if we can determine the crossing density from other methods, then we can determine the chi, which is the Florey-Huggins solvent polymer solvent interaction parameter. Okay, you can determine the crossing density using tensometer also. Okay, using tensometer. But since today we are not talking about instruments, so we will not discuss about the tensometer method. Okay, we only discuss about the solvent swelling method. Okay. So this is the, remember, this is the volume fractions and volume fraction, and this is the swelling ratio. Okay. So the relationship between chi and swelling ratio is given here. Experimental wise, we use a good solvent okay, for maximum swelling. And then we swell the rubber test piece in the dark for between 3 to 7 days. You can determine the maximum swelling by weighing the rubber gel, see whether any further increase in the swollen gel. Okay, so you dry the gel in the oven after 3 to 7 days. Okay, and then measure the dry weight. We don't measure the dry weight. We don't use the dry weight before swelling because some of the component may be soluble in the solvent. So you may have a little bit of weight loss. So we use the dry rubber weight after swelling test. So and then you weigh the weight of the solvent in the swollen rubber is given by the difference. Okay, the swollen weight and the dry weight. Okay, and therefore the volume fractions in the swollen state VR is given by the following equation. Very simple. Okay, we all know that fraction meaning what is the ratio, okay, of the rubber volume with regards to the total volume. Okay, so the total volume of the rubber plus volume of the solvent. Volume of the rubber is given by these expressions. Volume of the solvent is given by the expressions. Okay, and weight of the, I already explained this, so density, so on. So we just use this equation. Okay, and you can see here, this is a crossing density. Volume fraction is VR. We can calculate earlier on, right? Here from VR. Okay, so the rest are all known. Example, Vs is the molar volume of the solvent you can get from literature. Okay, molar. So the rest are chi you can get from literature. So this chi. So there are only 3 parameters you need to key in. 1, 2, 3. Then you can get the crossing density. And just a note, if you have high non-rubber material, for example, your zinc oxide is very high, your sulfur is high, or you have a lot of filler, then you got to deduct the volume from the dry rubber volume. So, for example, your zinc oxide, let's say you add 5 pHr. Okay, so out of 100 parts of rubber, you have 5 parts in zinc oxide. So you need to remove the volume of the zinc oxide from the dry rubber weight, dry rubber volume. Sorry. So of course the volume of the zinc oxide is equal to weight of the zinc oxide divided by the density of zinc oxide. Similarly, your filler, if you have filler, you use filler, then it will be weight of the dry filler that you use divided by the density of the filler. Okay, density of filler you can determine using the picnometer method or the suspension method also can. So the net volume of the dry rubber will be the gross dry weight after removing the solvent, subtracting the filler volume or zinc oxide volume or any other significant amount of non-rubber. You can try this out, see what is the significant contribution of each of these. Okay, you can do without subtractions and then you do again with subtraction. And what is the significant contribution of non-rubber fractions? Okay, so the gross dry rubber volume is the weight of the rubber divided by the density of the rubber. Okay, so total volume is the gross volume of the rubber plus volume of the solvent after swelling. What happens if you don't consider the filler effect. Because filler doesn't swell, right? If you use calcium carbonate or use silica, these are the things that you will not swell in solvent. Okay, it remain almost the same volume. So if you don't consider the effect of volume, you may lead you to overestimation of cross-link density. Okay? And you have to take note of this. Right? Consider the effect of non-swelling material in your rubber sample. Okay. So the way to calculate is very simple. Okay, you just use these expressions and substitute the figure that you have, the number that you have, you obtain experimentally, or you obtain from the literature. So this is an example. Okay, example: the swollen crossing nature rubber plus toluene is 0.5169 gram. Dry rubber weight after removing is 0.0958 gram. Molar volume toluene is given here. Density of rubber given here. Density of toluene given here. Polymer solvent interaction parameter is also given here. Okay. So since this is a workshop, maybe participants please work it out. What will be the crossing density by substituting all this number into the expression here. Okay, let's try it out. Maybe I give you 5 minutes to work out. Okay, since this is a workshop. Workshop means you must work lah. Or else it's just a lecture only. Or maybe I leave this during the break during the break better. We come back to this later on. You don't want to waste time. Okay, so I shall skip this one. Skip the answer. Okay, since we are only in the second part. Okay, solvent swelling, some practical notes. Use less volatile solvent because when you weigh the swollen gel, your volatile solvent may start to evaporate. Then you may not get a very stable reading. Use a less volatile. For example, toluene is not so volatile. Boiling point of toluene is about 111. So better solvent purity, better result, unless for comparison study. If you want absolute, better you distill your solvent. But it's just for comparison, then no need. Just compare A and B, so not necessary. Swelling in the dark to avoid degradation. Because light can induce degradation. Okay? Allow sufficient time to reach equilibrium. Repeat for a longer time to see any further swelling increase. Okay. So when non-rubber such as filler is significant, correction is needed. I already mentioned. Okay. Next, we go to the video. Share first. Okay, so to determine the crossing density of rubber, for example, nitrile rubber glove, we dip in solvent such as acetone. All right, and we cover it with rubber band. Right, and then we keep in the dark for 3 to 7 days. Okay, so after 3 to 7 days, we remove and we tap dry to remove the excess solvent. All right. Then we take the weight. After that, we remove this one from the balance and dry in the oven. So after drying for about half an hour, we dry in desiccator. So after cooling in desiccator, we remove it and take the weight again. Okay. And after drying, to make sure that the solvent is really evaporated, we move it, put in the oven again. Okay, so after the second drying, we take it out and we cool in desiccator. We take it out and measure the weight again to achieve constant weight. Very simple, right? Okay, the next will be the quiz. I want to put the two questions together. Original plan was to ask one by one, but a bit troublesome. The app doesn't allow too many. Okay, so participant get ready. I will share the screen. You can see the question, right? Just now I mentioned about tetra-functional network, okay? So what's the relationship between cross-link point and the average molecular weight of the rubber segment MC for tri-functional network? This is question 3. Based on the simplified Fourier-Renner equations, which of the following statements are correct? So I'll give everybody 5 minutes to answer the question. Those who got it right earlier on, you need not participate. Give the chance to other people. Okay, so can I give the answer now? Facilitator? Huh? I
All right,
better ask.
Doctor. We have the winners already. Okay, so we're gonna have top two winners. The first winner is Hwee, and the second winner is Daphne. Congratulations for both winners. If you can access the chat box, please provide your full name and phone number. Or if you are in group WhatsApp, we will approach you in the group WhatsApp for your details. All right, back to Doctor.
Okay, thank you very much. So I'll just briefly go through. I think this is quite simple. Okay. For trifunctional, what is fun network? What is the relationship between closing density point and average molecular weight of the rubber segment? Okay. Okay. let's go to this one. Okay, this one. So you can see here is a tetra functional. Okay, tetra functional. Tetra functional. Okay, this is 1 MC, 2 MC, 3 MC, 4 MC,
Doctor,
right?
are you
Yes.
sharing a slide?
Oh yeah, sorry. Can see now?
Yes.
Okay, sorry.
Thank you.
Okay, so we look at this one. You have 1 MC, 2 MC, 3 MC, 4 MC. Okay, so this is a tetra functional network. Okay, so 4 MC, how many crossing point you have? We have 1 here, right? Okay, how about this one? This one is share with the other one, so you only get half, right? So how about this one? This one is also share with the other 2, so you get half. So for 4 MC, you get 2 crossing point, right? 4 MC, 2 crossing point. Now, how about 3 tetra functional? Tetra functional, you have a T shape, right? So you don't have this. So this and this combined together, right? So this and this combined together. Okay. So 3 MC, you get how many? 3 MC, you get 2, right? Because this one is also sharing, this one is also sharing, right? 1/3, 1/3, 1/3. So you get 3 1/3, you get 1 crossing point plus this center one, another crossing point. So you have 3 MC, 2 crossing point. Okay. So I hope this is clear. Okay, so back to this question. This is also very simple. Okay, you just look at this, right? Swelling ratio increase. If this increase, if chi decrease, this will increase, right? So it's very simple. Okay. Of course, then the crossing density increase, swelling will decrease, isn't it? So this is a very straightforward kind of answer. Okay, before we take a break, any questions? Or we take a break first, then we Q&A. You get close to. Maybe we spend 10 minutes on Q&A, if any. Then we go for a break. Are they typing at the Q&A there? No.
Okay, Doctor, we have question.
Hmm?
Why we need to put the sample in the dark after adding the solvent?
Oh, I already explained, because the light can induce the degradation, so you get a higher swelling. Okay. So you need to put in the dark, because light can induce degradation.
Okay. So, and then what is the ideal temperature for drying the sample after swelling process? Ideal temperature.
That depends on your rubber sample and also the solvent that you use. For example, you're using acetone, then you don't need to be very high, right? You look at the boiling point of acetone is very low. Okay. So maybe slightly higher than the boiling point of the acetone is good enough. But if you use, let's say, higher boiling point or the evaporation, higher boiling point like toluene, maybe you need to set at or you can actually use vacuum, with that will be probably faster, right? It's okay one. You can use vacuum to suck dry, because the rubber will not get evaporated. Okay, you can use vacuum at low temperature, maybe 60. If you use pressure, if you use toluene, or you can use without reduced pressure, you can use say 100 to be sufficient. Okay, but make sure your rubber don't get degraded. You don't dry for too long. As to how long you need to dry, you need to check what is the optimum drying by checking the weight change.
Okay, next question is what is the difference between finding swelling index and cross-linking density? The method used is similar or not?
Oh, swelling ratio is just give you the relative, right? Relative kind of idea. So what is the crossing density and the swelling is given here. This is a swelling ratio and this is a crossing density. So this is a relationship. Okay, I've given you already. If you want to use swelling also can, but then just give you an idea, but you will not get the crossing density data. It just give okay, higher swelling mean lower crossing. Lower swelling mean higher crossing. That's all. Just for comparison. So you won't get any figure lah. You know, there's no value you can derive from without any calculations.
All right. How to calculate cross-linking density for composite gel?
Composite, then you a bit complicated lah. Depends on what kind of composite. For example, if let's say silica or calcium carbonate, then you need to remove the procedure is still the same, but you need to remove the volume of the volume fractions of the non-rubber. For example, you use silica, you use calcium carbonate. Then you need to subtract the volume of those non-rubber, as I said, for composite material. Okay, as I explained just now. Yeah. Any more? If there's no more questions, we go for break and then you as a homework, not really homework. You calculate the crossing density of just now given here. Okay, so here. Then we check compare the result with what I have here. Okay, I just stop sharing and then during the break there may be some commercial announcement. Okay, so with this, I hand over the session back to MC.
All right, thank you, Doctor. So for all participants, we will have a short break for about 15 minutes and we will be back later. Thank you.
15 minutes, so we come back 11:10.
Yes, Doctor. All right, participants, hope you guys are ready for our another session. All right. Now, I would like to invite Dr. Hwee for our second lecture. We will wait for the doctor a little bit. Hope you guys are ready.
I think we can continue.
All right, Doctor, the mic is yours.
So for the next two video clip, oh sorry, the first two, the last two sessions, you'll be on fractionations and molecular weight determination using viscometry method. So they are actually related. Share the screen. First, we ask about the fractionations of the rubber. You can see the slide moving. Okay. Why do we need to do fractionations? We need to separate the sample of broad molecular weight distribution into a narrow distribution, molecular weight distribution. The first one is to obtain structural information. Example, we want to know the branching of or the functional group distributions in different molecular weight. Okay. Second, obtain rubber with narrow molecular weight, I mentioned already. Okay. And to study the relationship between structure and the property. Because sometimes the molecular weight can influence the properties of the rubber, and we want to know to what extent the small or the big molecule impact the property of the rubber. Also is to understand the processing behavior of the rubber of different molecular weight. Okay. Let's say you receive a sample, you wouldn't know, right? What affect the processing behavior? Is it due to the presence of low molecular weight or the presence of molecular weight of too high, molecular weight too high? It may affect your processing behavior. Okay. Also is to elucidate the mechanism of rubber formation. For example, we want to know what is the end group, the terminal group, okay? In the low molecular weight of natural rubber. Because if you study the whole rubber, the terminal group or the end group concentration is too low. So we isolate the low molecular weight where we get high concentration of the end group. All right, because low molecular weight has higher concentration in end group, okay, or the terminal group. From there, it's more sensitive to in our analysis. Okay, if we analyze the whole rubber, maybe out of 5 to 10,000 repeating unit, you only get 2 or get 1. Okay, but if you narrow it down to a lower molecular weight, you can get a lot more, because lower molecular weight will give you higher concentration of the terminal group. Okay, that will give you a better sensitivity. Okay. And for understanding some physical properties such as solvent and oil resistance and crystallization and so on, okay, there are a lot more in terms of functional property of the rubber. Okay, so briefly, that will be the those are the objective that why we want to do fractionations. Okay, and also for molecular analysis, since we don't have gel permeation chromatograph, so we need to do this manually to separate various fractions of low different molecular weight and then determine the molecular weight of narrow distribution. Rubber molecules are more soluble at high temperature. Okay, so high molecular weight rubber of low polarity are less soluble. Okay, less soluble at low temperature in the presence of other polar solvent, or we call it poor solvent. Okay, since our rubber is non-polar, so poor solvent the polar solvent will be the poor solvent. Okay, so in the presence of poor solvent, it will cause precipitation of the high molecular weight rubber. Instant precipitation may be due to localized effect. If you add poor solvent into the solution of the rubber, immediately you get precipitation, but that precipitation may be due to localized effect. It may not represent the high molecular weight being precipitated out. Okay, so what we do is we increase the temperature to dissolve it into the solvent at high temperature, okay, of the precipitate rubber, and then we do a slow cooling. Okay, we do a slow cooling, and then the higher molecular weight rubber will become precipitated without the so-called localized effect. Moreover, it's not homogeneous. When you add the poor solvent to the rubber solution, the concentration surrounding the poor solvent is high, and they will cause precipitation of probably some low molecular weight rubber as well. Okay, so what we do is we redissolve it by increasing the temperature, and then we slowly cool it down over a long period of time, so that you get precipitated the high molecular weight rubber. Okay, experimental setup looks something like this. Okay, pointer out. Okay, so what you need is probably a pear-shaped kind of flask. Okay, maybe 2 neck. The side neck is for you to add poor solvent, and you have the folding propeller. Okay, folding propeller, so that you can insert through the small opening here. Okay, and this is an overhead connected to overhead stirrer, and of course it's rubber dissolved in a solvent. Example, measurable in taurine, and you have a thermometer to monitor the temperature. Also, the thermostat sensor and thermostatic water bath set at whatever temperature you reach. Okay, and here is a pour solvent for you to add dropwise. So while stirring, you add the pour solvent dropwisely, and then you stir. Okay, we continue stirring until substantial amount of rubber already precipitated. Then you stop. Okay, you stop, and then you stop adding the pour solvent, and you continue to stir. But this time you increase the temperature. Okay, let's say it's at 30, maybe you increase to 35. Okay, and you continue to stir, or maybe 37 until the rubber all dissolve back. Okay, dissolve back. So when the rubber dissolve at a higher temperature, you stop stirring. Okay, you stop stirring, and then you set your temperature back to 30. Okay, then you allow this water bath to cool down slowly overnight. Okay, cool down slowly overnight. Cool down slowly overnight so that the high molecular weight in this mixture of solvent will precipitated, and then okay, sink down to the bottom, something like this. Okay, so you notice when you stop stirring, folding propeller will stop. It will be folded. So the rubber will be precipitated, something like this. Okay. So when the rubber precipitated, you can remove the top part of the rubber solution and dissolve this precipitated rubber, because this is like a jelly look kind of rubber solution, rubber thick solution. You may need to add a little bit of solvent, okay, and then you precipitate in a poor solvent like methanol. Okay, then you get your first fractions of rubber. After isolating the first fraction, you pour back the top part of the rubber solution, and you continue. You repeat the procedures by adding full solvent and stirring. Then you get your second fractions and so on. Okay, so this is briefly describing how the accelerator procedures. Okay, so first we dissolve the raw rubber, example nature rubber, in a solvent. Okay, example taurine at 1% weight per volume. So we require this setup, and then we stir until it dissolve. Okay, normally take several hours, depends on how big is your sample. If you cut your rubber into small pieces, it will probably take faster. Okay, it will dissolve faster. But if you put one lump, then it will take longer time. Okay, you probably take overnight to dissolve. You cut it into very, very tiny pieces while stirring, then you add to it, you get more surface area, then it will dissolve faster. Normally, we do centrifugations to remove any gel or any heavy impurities like sand, all these material. Okay, gel particularly, because most rubber has a little bit of gel, some has high, gel. We can't use the gel because it's not soluble. You need to get a soluble rubber solution. So you can filter through a glass filter to remove the gel. But this is a little bit messy because your gel may jam out the filter. So, but if you don't have centrifuge, there's no choice, right? You have to use the filter to remove the rubber gel. Okay. To remove the rubber gel, actually you put a piece of a rubber sheet and then tighten it with a rubber band. Then you pull it out a little bit, allow air to go in, and then you close tight. So the elasticity of rubber will press the air and then the rubber solution through the filter. That will improve the flow of the rubber solution. Well, the rubber solution is very viscous, it take very, very long time to go through. So you need to apply some pressure, okay, to a rubber sheet, okay, airtight. On top, you press it down, or you don't even need to press down. You just allow some air to go in, and you expand the rubber sheet. Then you make it airtight with the pressure in the air trapped inside. Then you press it down automatically. Okay, so this is a way to filter it faster. So after filtering or centrifugating the rubber solution, you remove the gel. Maybe you go through the filter. Also, after centrifugation, then you transfer to a pear-shaped glassware, okay, container. So as shown earlier on, and then you place in a thermostat bath, set at 30, and then add pour solvent like methanol until it turns cloudy or some rubber become precipitated, shown earlier on. So you raise the temperature, water bath temperature, while stirring until the solution turns clear again, right? So you stop stirring and set the temperature back to 30 once you get the clear rubber solution. So allow it to cool to 30 overnight. Okay. Upon cooling, a small amount of rubber appear at the bottom of the flask, and remove the clear rubber, the top clear rubber solution, and then dissolve the rubber from the bottom fractions and add it to pour solvent with constant stirring. This one you probably know. And then we dry at reduced pressure. Okay, probably overnight. You can dry at 50 degrees C at reduced pressure. If you have a vacuum oven, if you don't have a vacuum oven, then you can dry in a desiccator with applying reduced pressure to a vacuum pump, vacuum chamber. This will make it faster. So this is normally we dry the rubber. We don't dry in the hot oven. Okay, high temperature. We will degrade the rubber. Okay, so this fraction is the highest molecular weight rubber, and then you pour back the solution on top, back to the container, and repeat the step above. So when no rubber precipitated at the end, you can concentrate the rubber solution by rotary evaporator. Okay, and then you repeat again, or if you don't want, then you can add pour solvent. Concentrate it, add to pour solvent, obtain the last fractions. Depends, if you want more fraction, then you need to concentrate it to remove the non-rubber, make it thicker, and then you can continue to get more fraction out of it. If you don't want, then just concentrate and pour into the pour solvent, get the last fraction. Okay, so experimental why is quite simple. All right. So this process flow, if it's a rubber, you remove the gel, add pour solvent with stirring, so until the rubber appear or precipitated or it turn cloudy. So you increase the temperature to dissolve the precipitated rubber. Then you slow cooling to precipitate the rubber. Okay. Then you remove the clear rubber solution, dissolve the precipitate rubber in solvent again, then reprecipitated in excess poor solvent and dry rubber under dispersion. So this is a process flow. Example of applications. For example, if you detect aldehyde group, let's say in natural rubber, you want to know whether this aldehyde group is it due to degradation, okay? Degradation of the rubber. You see on the right hand side here, you can see degradation of rubber normally produce aldehyde group, okay? But because it's already in broken chain, appear the functional group aldehyde group in a broken chain. So you normally expect your aldehyde group to be in the low molecular weight fractions, right? High molecular weight, you wouldn't expect high aldehyde content. You expect if it's due to degradation, then we should find this in the low molecular weight fraction. So when we did the fractionation, okay, you get fraction 1, 2, 3, 4. Then we determine the aldehyde group, okay. And you can see here, okay, actually high molecular weight, the first second has a high aldehyde group. Low molecular weight has a low aldehyde group. So this will tell us that actually the aldehyde group is not originated from degradation reactions, okay? Or else we will expected low molecular weight to have high aldehyde content, not the other way around, okay? Since high molecular weight contain high aldehyde content, we can conclude that it is not due to degradation, it is due to some kind of mechanism that maybe enzymatic action of rubber or the olefinic group attached to the rubber that form the aldehyde group during the formation of rubber, something like that. Okay, so this is how we want to make use of fractionation to obtain more information, okay, for different fractions of rubber. All right. Okay, fractionation of rubber, some practical note. Okay, so we use only the soluble fractions. Okay, and rubber concentration should not be too high. Too high, then immediately you get precipitated very fast. Okay, so that is not the actual what they call non-rubber volume that the post solvent that you need. So normally we use about 1%. Okay, but it depends on the molecular weight also. If too thick, then it's very difficult to stir. But 1% is, but if the molecular weight is too very low, you can increase it. The point is we don't want it to be too viscous. Too viscous, very difficult to handle. Fraction weight depends on the molecular weight distribution. Okay, how much you get from each fraction depends on the distribution. If the distribution is skewed toward high molecular weight, then you get higher weight from the high molecular weight. Amount of post solvent needed is by experience. You do a few times, you know how much you need to add and then when you need to stop adding. So addition to allow good mixing, okay, to prevent precipitation of the large amount of the rubber. If we add too much, then a lot of rubber will come out. Then you know you add too much already. You don't want one fraction to have very, very high amount of rubber and the other fraction got very little rubber. That's not very evenly distributed. Reprecipitation of isolated rubber to remove the mixed low molecular weight rubber. There will be some low molecular weight mixed together when you isolate the precipitated rubber. Okay? So that's why we need to reprecipitate it. Here, there will be a little bit of low molecular weight and other molecular weight mixed together here because you never get a pure one. That's why with the low molecular one, you reprecipitate it, mix into this fraction you will remove them, okay, in the reprecipitation process. Okay. Antioxidant may be added to prevent degradation. If your rubber sample is very sensitive to oxidations, okay, you may not add a little bit antioxidant. Okay. If it does not interfere your subsequent test result, okay. If it does, then you cannot use. Also, when you want to wait for it, you wait overnight for the rubber to precipitate. Maybe you want to cover it aluminum foil, okay, to avoid exposing to light. Because light can induce degradations when the rubber is in the solvent, very easily degraded. It's important. Another point is if you use a thermocouple or the thermostat sensor, make sure you clip nicely your sensor to the container or to the retort stand or whatever. Make sure this sensor is in the water bath. Okay, if you use, of course, you use a water bath come with a built-in sensor, then it's okay lah. Right? But if this thermocouple sensor, if it's a separate entity, then you better make sure it fixed at certain place, so that you will not drop out from the water bath. What happens if this one drop out from the water bath? Then you have problem. When this sensor come out, meaning your room temperature is very low, so the heating continue to occur until this water bath get dry and it cause fire. So it's very important. It happened before, someone, the student, not very careful, didn't attach this properly. So this one actually dropped out from the water bath. Then the heater here will sense that, oh, the temperature is low because outside temperature is low. So they continue to heat the water bath until it get dry. If let's say you do the experiment on Friday, you will come back on Monday. Then over weekend, this water bath will get heated continuously over 2-3 days. Eventually get dry, and then it continue to heat again, it cause fire. Okay, so I'll be very, very careful. So it happened before. All right, that's about it. I think very simple. Unfortunately, for this experiment, we have problem getting the right setup. So the experiment is rather short. I stop sharing first. Make sure this sound is on. Okay. So to fractionate, this is a rubber solution. We add poor solvent like methanol. All right, so it's a very short video clip. Okay, I need to put question 4 and 5 together. 5 and so it's only one question. Okay, this one. Okay, then never mind. So I will show the questions. So this time we only have one question. Okay. Share. Okay, get ready to answer. Long sentences.
All right, Doctor, we already have the winner.
Okay, good.
All right, so for this quiz, our winner is Wen Ting Chao. Congratulations. All right, back to Doctor.
Okay, thank you very much. So, okay, I will discuss the questions now. In the fractionation of rubber experiment, which of the following statements are true? When the water bar temperature is gradually increased to redissolve precipitate rubber, low molecular weight, because solubility will be better for low molecular weight. Okay, so low molecular will dissolve first. Okay, so the correct one is number 2. So when the rubber strain is added to excess poor solvent, the lower molecule may not be precipitated if the concentration is too high. Okay, which is true because solubility is high. Okay, solubility is high for low molecular weight rubber. So you add poor solvent, it may not come out, but the highest molecular weight one will come out. Okay, so the answer is 2 and 3, which is C. Thank you very much. Next, we move to Q&A. Anybody have any questions? No questions? Probably you have not used this technique before. Yes.
Participants wants to ask a question, you may raise your hand or maybe you can ask.
Yeah, you can ask directly.
Directly.
No problem. Yeah, no need to type. Okay. Ask any question you like. Just for the information, all those I shared today, I used this technique before, okay, and in my study. So I share with you since I already retired. So part of my contribution, hopefully you can pick this up and use in your work or in your study as well. Okay, hopefully they're useful. But nowadays we have highly sophisticated instrument. Okay, so maybe fractionation may not be very relevant, but still, if you want to study, for example, the end group, the terminal group of a molecule, of a rubber molecule, or any polymer, okay. Let's say you want to send to NMR for analysis of the structure. It is better if you do fractionations. Okay, if the molecule is too high. Okay, if the molecule is too high, you get very poor sensitivity in terms of the low concentration component. Example, the end group or the branching or the crossing point, all this, they are very low in concentration, very difficult to detect. Okay, and if you send for NMR analysis, you won't get the very good signal. Okay, for the end group or the terminal group or the crossing point. Sometimes you want to look at what is the structure of the crossing point. Okay, by using NMR. Okay. It is better to do fractionations and isolate this lowest molecular weight, and that's where you can get a very good sensitivity in your analysis. All right, so that's the advice in your study. In fact, I use this technique to detect the terminal group of natural rubber molecule. Natural rubber molecule, the molecule is several millions. Okay, several millions to several 10 millions. Okay. So for such a high molecular weight, you want to determine what is the structure of the terminal group. Okay. Out of probably 5 to 10,000 repeating, you only get one. you only get one terminal group. So 1 in 10,000 is very, very difficult to detect. You know, you send whatever, you know, technique also very difficult, you know, 1 in 10,000. So by doing fractionation, we can get a better signal in the analysis of the terminal group or the branching point. Okay, sometimes you do branching point analysis. What is the structure of branching point? Okay. All right. If there's no question, then we will move on to the next one. That will be the final one. Okay. The final one, we will have another 2 questions. Then we conclude our today's workshop. All right. The final one will be the molecular weight analysis using viscometry methods. Okay, viscometry methods. This is also what I study when I was a student. Okay, when I was a student, I use this technique together with the fractionation. So it's not that we didn't have GPC. Actually, GPC have limitation. Okay, GPC have limitation. Because of high shearing, sometimes it can cause degradation in GPC. You know, of course, in GPC is very convenient. You just inject one time, you get all the information out. Right? It's very convenient. So, viscometry maybe not popular these days, but for those who do not have GPC, you know, gel formation chromatograph, and you can do viscometry methods. Okay, and in fact, viscometry can give you more information also. Okay, we will look at this later on. So intrinsic viscosity or IV is a measure of a polymer molecular weight. It reflects the material, melting point, crystallinity, tensile strength, and so on. So the molecular weight can be related to glass transition temperature, okay, by this equation. Okay? So this is the glass transition temperature of a molecule with infinite molecular weight, and this is a molecular weight, and this is a constant. So as you can see, with the higher molecular weight, the higher the glass transition temperature. Okay. Significantly affect the physical, such as softness, hardness, and mechanical property and processability of the material. Example is you can see a recent patents on a better tensile with bimodal distribution of polysulfide rubber in our text. Okay, you can see the recent patents. Okay, in the abstract mentions that it contains a low molecular weight polysulfide of less than 1 million at a content of 10 to 70% by weight, and a high molecular weight polysulfide of 1 million or and above at a content of 30 to 90% by weight. See? So you can see here is an example how molecular weight impact the performance of the material. Okay? By using exclusively high molecular weight or exclusively low molecular may not give you the optimum performance. Sometimes you need to have a mix of both high and low molecular weight. Okay? So if you do not analyze the raw material that you use or the raw material that you receive, then you wouldn't know, right? What's the distribution? How much? What is the content of a high molecular weight? What's the content of low molecular weight? Okay, so objective is to measure the intrinsic viscosity of the rubber or any polymer solution and calculate the molecular weight from the intrinsic viscosity data and the mark Hwee constants to determine the hugging constants and determine the relationship with the rubber or the polymer branching. Okay. Experimental wise, of course, we still need a water bath. Like before, we need to have a thermostat sensor. This is developed viscometer. Okay, a water bath. And as before, we need to remove the gel. We need to remove the impurity this time, not just gel. This is this is a must. To do viscosity measurement using capillary viscometer, you have to filter using glass filter. Cannot skip this because most samples are full of dust. We cannot have dust in the sample here. Okay. So you must filter. To dissolve it, you have to filter like as described. You wrap it with a rubber sheet like a glove. Then you tie it with a rubber band. Make sure it's airtight. And then you pull up and release a bit of air, allow it to go in, and then you close it. Then you release the rubber glove, allow it to, or rubber sheet to allow the pressure of the trapped air to press for you, or you can press yourself also can, press, so that you can squeeze out through the filter. Okay. After that, you pour the rubber solution through the opening here. Okay. Better to have what they call quick fit joint here. Actually, these two on the two on the left, because later we need to close this opening, and this one. This one is for you to pump the solution up. Okay, to pump the solution out, you need to close this opening. Okay, you pump to here, or else you pump, then the solution will shoot up. Then you fail already. When the solution overflow from the viscometer, then the whole experiment is failed. So, if possible, you have a quick fit joint here so that you can close it airtight, so that the solution will not shoot up. So normally apply compressed air. Any compressed air will do. Again, more convenient to have a quick fit joint here, so that you tightly fitted this here. And then you close this one so that you press exert pressure on the solution, so that the rubber solution is still going up here. You go up here, because here is closed. Go up. So there are two levels here. Okay. So you allow it to move up. Maybe before this round, what we call, because we need to measure the flow time from here to here. So the excess volume here is to prevent the solution suddenly shoot up. So this will give you more volume. So when the solution goes above the level, you can stop. Now after stopping, you cannot remove this first. You cannot release this. So you have to release the pressure first. release the pressure on the extreme left. Okay, you remove already, and then you remove the cover, variable cover at the center here. From there, the solution will flow down. Okay, go down. Then once you reach a level, there's a marking here. Then you start your timer, and then when you reach a second marking here, then you stop the timer. So you measure the flow time from here to here. Okay. So this is briefly the procedure of measuring the viscosity using the envelope viscometer. Now, how expensive is this viscometer? I went and checked. You can see this website is only about 100 ringgit only for this viscometer. So it's very relatively cheap. Okay. You can even buy yourself and do it at home. Only 100 ringgit. Huh? So it's very cheap, but you don't have water bath, what they call for constant temperature. So it's relatively cheap nowadays. Especially you have a lot of what they call supplier, and then they can make it very cheap. And this is what I described just now. So there are two labels here, A and B, the mark. So when the solution flow up to here, this reservoir here, you should stop, or you continue to shoot up. Then you overflow. Once the overflow, you cannot consider fail. Okay. So the description is first dissolve the rubber, and then this time we use a more diluted and filter, use glass filter, pour solvent to into the viscometer via the opening one here. Okay, and then allow the liquid temperature to reach equilibrium in the water bath. Here again, temperature is important. Okay, you want to measure at certain specific temperature. Your temperature can affect the viscosity of the rubber solution. Okay, you must reach constant temperature. Or every time you repeat, you get a different flow time. Okay, we're supposed to get constant flow time each time you repeat. Right? If every time you get a different reading, then which means something is not right. Okay, something is not right. Maybe your rubber solution is not clean. A lot of dust inside there. So first we need to shut the opening number 2 here. Okay, they apply pressure, positive pressure via any compressed gas to opening 1. Okay, so to pump the liquid up. Okay, to level in the 3 here, up to level above level A here, and there's a marking here. So as I mentioned earlier, for easy operation, modify 1 and 2 to quick fit joints. They will ease the operations. Okay, release the pressure on 1 first. Pressure 1 first, release, and then open 2. You remove 2, any cover or any joint, quick fit joint. You remove 2. Then measure the flow time when the solution drop from A to B. Okay, set at 30 degrees C or whatever temperature you want to use. Okay, normally above 25, because if you set too low, then you need cooling, right? You need cooling already. So cooling is a bit troublesome. So it's set above 30 if you are in aircon room. Aircon room normally is 20, 25. So you perform heating instead. So heating is better. If you need cooling of the water bath, then it's more troublesome. You need to have a compressor already. with the cooling unit together with the heating. So it's a bit troublesome. But anyway, you can still perform at 25 if you wish. Okay, can perform at 25 if you wish. Okay, so you repeat several times to obtain consistent reading. You repeat A to B, A to B several times as be consistent. If it's not consistent, means in most cases your rubber solution has is dirty, got some impurities, some dirt inside them. So that will also means a failure. So two things need to remember: don't allow the solution to overflow. Okay. Second, must be clean. The solution must be clean. So you calculate the specific viscosity. Okay. By subtracting it from the flow of the solvent, pure solvent. First you do pure solvent and then you do rubber. You be careful when you do solvent. You do solvent, you have to dry your viscometer. So all these are in capillary. So if your viscometer is wet, then when you add rubber, then your concentration is out already. Concentration is out. So divide by the flow time of the pure solvent. Similarly, when you want to clean it, you need to make sure it's thoroughly clean, no rubber trap anywhere in the viscometer. Normally we rinse thoroughly. Also, when you want to do dilution, meaning more diluted, you need to rinse it several times, or else there will be a previous concentrated rubber trapped somewhere on the surface of the glass. Right, so you need to pump up, let it flow down, pump up, let it flow down several times before you take the measurements. Okay. You want to let it flow fast, okay, now you apply gas here. But you need to be very careful. Don't, when it close to low level, you should stop. So they let it flow down. If you want it to accelerate the flow for cleaning. Okay, so from the Hugging equations given here, okay, so this is the intrinsic viscosity, K prime is Hugging constant, and this is specific viscosity. Relative viscosity is given like this. Viscosity of rubber solution in solvent is shown here. So this is the pure solvent viscosity. When we say viscosity, actually it's the flow time. So in practice, this is the flow time of the rubber versus divided by flow time of the solvent. For specific viscosity, then it is flow time of the different divided by flow time of pure solvents. Okay. I think that's all. So you just measure the flow time and just calculate the relative specific viscosity. Liter Sp divided by the concentration. The concentration is in gram per deciliter. Okay, gram per deciliter. So as we know, you just plot this one versus the concentration, right? So this will give you the intercept of an intrinsic viscosity, and this is the gradient, right? The whole expression here is your gradient. Okay, because you plot this against the concentration. Okay, so you can calculate the kappa prime, the Hugging constant from the gradient. Okay, it's quite straightforward to do. Not very difficult. So data processing from the Mark-Hwee constants of Mark-Hwee equations. You have this intrinsic viscosity equal to kappa molecular average viscosity average. Average viscosity molecular weight. Okay, power of A. So K and A are actually Mark-Hwee constant. Okay, MV is a viscosity average molecular weight. So we can calculate if we know K and A. Okay, from the literature you can get. So you get the value from the literature first before you set the temperature, or else when you determine your own temperature, then you go and search the literature, then you discover it. There's no K and A in the literature for that particular temperature. Then you cannot calculate. Go to the literature and search for K and A first. At what temperature we have K and A. Okay. Or if you have other method of determining the molecular weight for fractionated rubber, then you can use that value to obtain K and A value. If you have the molecular fractionated rubber, maybe you inject into GPC. From there you can calculate the K and A value. Okay, by plotting this from this equation. Okay, log intrinsic viscosity, okay, versus log molecular weight. Then you can get. So for polydispersed rubber, your number average is smaller than viscosity average. Viscosity average actually is lower than weight average. Number average is divided by number. Weight average is divided by weight. You notice here. So they will give you the. You can go to literature and search what is, or internet and search what is weight average, and what is a number average, what is weight average for molecular weight. Okay, so the viscosity average actually is in between these two. These two are normally used, number average and weight average. Okay, so for fractionated sample, we narrow molecular weight distribution. We can say that they are all equal. They are all equal, or close to each other. If not, they are very close to each other, because you can assume to be equal. The degree of polymerization equal to molecular weight, okay, divided by molecular weight of the repeating unit. Okay, and Hwee constant is independent of molecular weight, but it increases with decreasing solvent power. It increases with branching. If your branching concentration is high, the K prime value will show an increase. Okay, this is based on the reported in the literature. Okay, example of applications. Okay, so we have intrinsic viscosity determined for different weight fractions for the fractionated rubber, and we determine, let's say, using osmometry, the number average molecular weight. We can also determine using NMR. From there we can calculate branching, okay, from these two. So we compare. So this is what we obtain using different technique, and compare. Whether Hwee constant really increase with the branching. Now this is just to compare. Okay. So from here we can see fraction 4, 0.4, fraction 1, 0.8. You can see. So actually correspond to the branching. We can use the Hugging constant to indicate qualitatively, if not quantitative. Quantitative, of course, you need to use other techniques like NMR or sumatometry or this, to get the actual branching point concentration. But just based on Hugging constant alone, you can conclude that actually there are branching in the higher branching point in the higher molecular fraction, and lower branching in the lower molecular fractions. Okay. And another point is, okay, let's say you obtain a molecular using osmometry, you can determine K and A value, okay? Or you can get it from GPC, right? Then you have viscometry from a viscosity, and you have from other methods. From there, you can determine the K and A value yourself, okay, by plotting log intrinsic viscosity versus log M. Okay, then you get the intercept as log K and gradient as an A value. Okay, so here you can see is quite useful if you don't have GPC, you don't have NMR, you don't have osmometer. You can still get some qualitative indication, maybe good enough for your publications, right? If you don't have any instrument, just by doing viscosity measurement and also the what we call molecular viscosity average molecular weight, you can also publish some of your research finding, even though you may not have a good lab setup, okay, or facility. So this is what I did. Okay, for 4 fraction, you get a straight line, and then we can determine the what you call the K value and the A value. Comparing it with the literature, you can see they are very close. Right? Literature, they use other methods. Okay? So the example, you get about 3, this one 3.3, it's about 10% different, 30.74, and this is 0.71. Okay, so you can see viscometry method actually can be useful, right? Some practical notes on the with intrinsic viscosity measurement. Use only soluble fractions. Use only soluble fractions. Filter the rubber. Okay. Filter rubber concentration should be less than 0.5. But it depends on the viscosity. If you find very viscous, then you may need to use lower. If you find it maybe not so viscous, you can use slightly higher. Okay. But generally, the guideline is 0.5% weight over volume. Must use filtered rubber solutions. Okay. Unfiltered will land you problem. Okay. Must be dust free. Must be filtered. And then make sure there's all your container, everything you filter already, your container must be very, very clean. Okay. Because when you filter your rubber solution, if the receiving container is dirty with the dust, then it's also pointless, right? You remove the dust, but your container to receive the filter rubber solution is also not dust free. Then you defeat the purpose of filtering it, isn't it? So everything must be thoroughly checked, no dust. Only you can use. Same thing go to your viscometer, must be dust free. Because dust causes inconsistent flow time. When you inconsistent flow, very highly likely it's due to the dust present in your in your rubber solution. Okay. When this happens, your experiment is considered failed. You got to do everything all again, clean up your viscometer, everything, you know. So troublesome. And viscometer should not be dry in oven. So just blow dry is the best. Maybe use a compressed air to blow dry. Okay. Don't dry in, because glass can deform. Okay. The glass can deform, especially capillary. So if they deform, then next time you measure again, you cannot compare. Okay. Then it become apple orange comparison. Okay. Make sure don't dry it in the oven. Okay, so we have a video presentation on intrinsic viscosity, and it's very short also. Okay. I stop sharing first. Go to the video clip. Then I share. Oops. Turn on the computer sound. Okay. Dissolve the rubber in the toluene solution. Okay. And then before we measure for viscosity, we have to filter the rubber solution by filtering through the sintered glass filter. Okay. We apply rubber force on top so that it can flow faster by exerting the pressure. So that the solution can flow faster. Dissolve rubber in a solvent, we just pour into the viscometer. All right. And then we place in the thermostated bath. Set at 30 degrees C. Okay, that was a short video clip. My apology, I forgot to show the how I pump the rubber solution up because it was not very well pumped, so I didn't sort of show you. Not very presentable, so okay. Next one will be the question time, right? Let me the two questions together. Okay. Questions are ready. I will share. I hope you can see, right?